This video is about to identify resistors in series and parallel to calculate the corresponding resistance for each connections. Then, two EMFs are introduced to this circuit, and the Kirchhoff first and second laws are applied to determine the relationship between all EMFs, resistors, and currents. So this is the network of circuits and is asking the total resistance in terms of R between points A and C. So between A and C, we have just one resistor. So the resistance here is just R. Between B and X, we have two resistors. Between B and X, we just have those two resistors. For these two resistors in parallel, the inverse of the total resistance is equal to the sum of the inverse of individual resistors. So in this case, we have the common denominator R. So R divided by R is 1. R divided by R is 1. So now we have 2 over R. So 1 over the total resistance is equal to 2 over R. Now I'm going to flip both fractions. So the total resistance is equal to R divided by 2, or 0.5 R. The last one, we need to find the total resistance from A to Z. So all is included. So we have here those two resistors in parallel, and the result is in series with this and this. So the total resistance is R plus those two in parallel is exactly 0.5 R plus this R. So when we add them, we have 2.5 R. Now this is our original circuit, and this is the same circuit, but now with two cells or two batteries. The first question is, we are going to use the Kirchhoff laws to find the relationship between the currents I1, I2, and I3. To find the relationship between all three currents, let's use Kirchhoff's first law, which means the sum of all currents in a joint is equal to the sum of all currents out. So we have here, going in, we have I3, in and out we have I1, and we have I2. If you want to check on this side, we can use the same approach. The sum of currents in this case is I1, and we have I2 is equal to the sum of currents out, in this case is just 1, I3. So the equations are the same. So to answer the first question, I3 is equal I1 plus I2. Now this question is asking to find the relationship between a E2, R, I2, and I3 in the loop B, C, X, Y, B. B, C, X, Y, back to B, this loop. Before applying Kirchhoff's second law, we need to determine the path of our loop. In this case, we have this battery here to guide us. So this is minus, this is plus. So my loop is going from the negative side of the battery to the positive one, like this. Kirchhoff's second law states that the sum of all EMF of a loop, of a closed loop, is equal to the sum of all the PDs in the same loop. So the EMF, I just have one, E2 equal. Now the PD. The PD, you need to look at the direction of the current and the direction of my path. In this case here, we have this R with I3. The question is positive or negative? Well, is it the same direction as my loop? So go like this, and the current is this way. So this is positive. The second one also the same direction of my path. I2, the direction of the path of my loop. So that will be plus R, I2. So to answer the question, this question with the green loop, since R is a common denominator for common term for both, so we can arrange the equation and present this way. Now the next loop is A, B, C, X, Y, Z, A. So A, B, C, X, Y, Z, A. So this is the orange loop corresponds to this question. We are going to use Kirchhoff's second law for the orange loop as well. But before, we need to determine the path of the loop. So I'm going to be guided by this one here. Again, the direction of the path is arbitrary. So from negative to positive, and I'm gonna do my loop this way, the external one, like this. To make it easier for me to determine if it will be a positive or negative PD, I'm going to write the current over the resistor with the direction. So this is my I1. And this one here is also I1. Same one, because they are in the same side of the loop, I1. Now I have two EMFs. So my first one, because it's the direction of my path, negative with positive, so E1 is positive. The second one, I'm going from positive to negative. It's the opposite that I did here, that this is my reference as positive. So this one will be my negative, E2. Is equal to, now let's work with the PDs. So my path is down here, is the same path of the current, so that will be positive R, I1. This one, the next one is this, so it's the opposite direction of my path, so negative R, I2. And my last one is this, is the same direction of my path. So plus R, I1, one more time. And I close the loop right here. So this equation can be rewritten this way. E1 minus E2 is equal. Those two, I can add them. 2R, I1 minus R, I2. R is a common term, so I can rewrite it this way, and that will be my final equation that relates all those variables. If you have decided to go to the opposite direction of the path of this loop, like instead of going anti-clockwise, you go clockwise, and then all that is going to happen is the order is going to change, but the value of the result, like in terms of magnitude, will be exactly the same. Correct and correct.